Hello, we meet again and continue with question number 18. Okay, now we have a metal block P of mass 500 gram. Okay, so the mass of this metal block P is 500 gram, or maybe I just put this in kilogram, that would be 0.5 kilogram. Is heated in the boiling water at the temperature of 100 degrees Celsius. So here the temperature is 100 degree Celsius. All right, so that would be the initial temperature for the metal block P, 100 degree Celsius. Transferred into the water. Okay, and then this water, it is said that the temperature here, so I will just write here the initial temperature of the water is 30 degrees Celsius, and then the mass of the water in the polystyrene is 250. So here I have the mass 250 gram, or equivalent to 0.25 kilogram. And then after 2 minutes, the water temperature rises to 42 degrees Celsius. Okay, so the time is 2 minutes, so that would be 120 seconds, and the water rises to 42 degrees Celsius. Right, so our final temperature for the water is 42 degrees Celsius, or maybe I should write it here. Okay, the final temperature is 42 degree Celsius. Alright, so who supply heat and who receive heat? So heat is supplied by block P and received by the water. Alright, so the quantity of heat gained by the water in the polystyrene cup, or quantity of heat, so I have Q equals mc theta. And what is my m? M is 0.25 kilogram, right? Okay, so we are talking about the water in the polystyrene. So this water here, so the mass is 0.25, and then our specific heat capacity of water is given in the question. That will be 4200, and then the change in the temperature, I know that theta equal to the final temperature minus initial temperature. Final temperature is 42, initial is 30, so the difference is 12. Okay, 12 degree Celsius. So here multiply by 12. So you do your calculation, you should be able to get this 12,600 joule. Okay, or you can also write this as 1.26 times 10 to the power of 4 joule. All right, that is question number 1. So let's move to the next question. The rate of heat supplied to the water. Okay, the rate of heat supplied. So our Q just now, we have found out it to be 12,600 joule, right? And then the time, remember, it's 2 minutes, is 120 seconds. So the rate of heat supply, right? So the rate of heat supply, that will be very easy. Just take the heat and then we divide by time. So Q over T. So here I have 12,600 divided by the time 120. So you will have 105. Okay, up here is joule, right? And down here is second. So I have joule per second. Okay, can you follow the discussion? Alright, so we go to C, the specific heat capacity of the metal block P. Okay, I want to know what is the value of this C. Okay, the specific heat capacity of the metal block. Okay, what do I know about this? I do know that the Q, the heat from the block, okay, from the block is transferred and received by the water. So Q of water, okay, they must be the same. And Q of block, that will be MC theta, okay. And this one here we have calculated it just now to be 1.26 times 10 to the power of 4, right? Okay, what is the mass of the block? Okay, the mass is 0.5 kilogram. C is what we want to find out, and then remember our theta here, okay? Theta equal to final temperature minus initial temperature. Okay, what is our final temperature? 42, right? So it is 42 is our final temperature, and then our initial temperature is 100. So can you see that this will become negative? So just to make our calculation easier, not dealing with negative value, okay, even though actually it is supposed to be a negative because heat absorbed and heat release. So here you will get this one here to be 58 degrees Celsius. So I just put my theta here to be 58. Okay, equals 1.26 times 10 to the power of 4. Alright, so calculate your C. You should be able to get 434.5 joule per kilogram per degree Celsius. Okay, so that is the specific heat capacity of the metal block. Okay, try to understand what we have done here. All right, so at this point here, actually I am using my principle of conservation of energy. What is given, that is what is taken, right? Given by the block, taken by the water, with the same amount of Q. Okay, so let's move to question number 19. I have a student performs an experiment to investigate energy change in a system. So he prepares a cardboard. Okay, the length of this cardboard is 50 cm, and then the lead shot here is 5 centimeter. So meaning to say this lead, okay, this lead shot is, if we invert the tube, it will travel from here, correct, from here to here. Okay, what is the distance here? So the distance here must be 50 minus 5. So the distance traveled would be 45 centimeter. Okay, does that make sense? All right, and then here it says that invert 100 times. All right, so we keep this in mind in our calculation. All right, and the mass of the lead shot is 500 gram. So the mass of this lead shot here, the mass is 500 gram, or equivalent to 0.5 kilogram. Okay, now let's answer the question. State the energy change, okay, each time the tube is inverted. Well, that would be easy. That would be gravitational, okay, gravitational potential energy right, will be converted into kinetic energy. Okay, the lead shot will fall from up here going down. Okay, up here definitely it will have the gravitational potential energy due to the height, and then it travel down. when it travels down, it must have what we call the kinetic energy. It's due to the motion of going down. Alright, so what is the average distance taken by the lead shot each time the tube is inverted? So we have answered this. That will be the length of the tube is 50 centimeter minus the length of the lead shot itself, which is 5 centimeter. So the average distance traveled would be 45 centimeter. Simple. Okay, now calculate the time taken by the lead shot to fall from the top to the bottom of the tube. Okay, so I have a lead shot up here, falls down, right? So it falls down. So the S, the height or the distance travel, that would be 45 centimeter, which is 0.45 meter. It falls down with the gravitational acceleration. That will be g, a equal to g, that will be 10 meter per second square. Alright, so can you see where I'm leading you to? Alright, so it is about our linear equation for linear motion. Okay, so remember this equation, S equals ut plus 1 over 2 at square, because we want to find what is the time taken. Okay, what is S? S will be the distance traveled, right? It's 0.45 meter. Okay, so I am going to write here 0.45. Initial velocity, that is 0. Okay, initially it is up here, it's not moving yet, so the initial velocity must be 0. Okay, so u is 0 up here. All right, so it's 0 here, plus 1 over 2. A would be the gravitational acceleration, that would be 10 multiplied by t square. So calculate for t, solve for t. You should be able to get your t equals 0.3 second. Okay, can you follow? All right, so let's go to D. After inverting the tube 100 times, the temperature of the lead shot is found to have increased by 3 degrees Celsius. Okay, increase by, okay, so this must be our theta. Okay, whereby theta equal to the final temperature minus initial temperature, and this equals 3 degrees Celsius. Alright, now calculate the work done on the lead shot. Alright, this is simple. Remember that work and energy, they are interrelated. Okay, so what work do I have? I have mgh, right? I have gravitational potential energy. So I'm not going to use my kinetic energy, because in using that I need to find my velocity, right? So if you recall this thing here, it from a height falls down, okay, from a height, and then it falls down, okay, to the ground. So here I have mgh plus 1 over 2 mv square, and then down here I also have mgh plus 1 over 2 mv square, but up here my velocity is 0, not yet moving, so I only have my potential energy, and down here my h is 0, so I don't have my gravitational energy, I only have my kinetic energy. But using the principle of energy conservation, these two values must be equal. Okay, these two must be equal. Alright, so if that's the case, then I'm going to use my gravitational potential energy to be equated, to be equal to my work. Okay, so work is energy. So energy here, I'm going to use my gravitational potential energy, but notice that inverted 100 times. So I have to multiply here by 100. Okay, now let us finish up the calculation. So I have here 100. The mass is 0.5. Gravity is 10, and then the height is 0.45. The distance travel. Okay, so you do your calculation, you should be able to get the answer here would be 225 joule. Okay, so that is work done. Right, next, calculate the specific heat capacity of the lead. Okay, so work done. Okay, we have seen the work done just now. It is mc theta. Okay, so maybe I write here work done. Okay, will be transformed into heat. Okay, well, this is from our principle of energy conservation. So the work done just now is 2 to 5, and then our q is mc theta. Okay, remember that our q is in joule, right? And then work is also in joule. Q is our heat energy. All right, you see here, so they are the same thing. So 2 to 5 equal mc theta. All right, so I have here 2 to 5 work done equal mass of the lead. Okay, the mass of the lead is 0.5 kilogram. Okay, and then multiply by the c, and then theta is, if we go up here, it is mentioned in the question, increase by 3 degrees Celsius, so our theta is 3 degrees Celsius. All right, so here is 3. Okay, do you follow? So calculate c, you will get 150 joule per kilogram per degree Celsius. That is the specific heat capacity of the lead. Alright, so remember that this is work, work done. Okay, now 3. State the assumption used in your calculation. Remember what I mentioned? Alright, anything dealing with energy, if you are asked the questions of what is your assumption, so the answer must be no heat loss, okay, to the surrounding. This is the magic answer. Alright, I hope you can follow. Alright, so we move on to question number 20. Diagram shows two identical metal balls, okay, heated for a few minutes in boiling water and then transferred into two beakers containing liquid X and liquid Y. So meaning to say that initially the temperature of these two balls must be the same. Alright, two identical metal balls. Well, it's okay. So we look at the diagram B and diagram C. Okay, the initial reading on the thermometer when the of this liquid here is 25. Final reading is 40. So I can see that the temperature, okay, the difference in the temperature is about 15, right? Increased by 15 degrees Celsius. But in a liquid Y, I can see that the difference in the temperature is only 5 degree Celsius. So this one increase more, this one increase less. Okay, that is from the diagram. So let's go on with the question, but before that we are also given the table, right? So the mass is 300 and then the specific heat capacity of x and y. Okay, x and y are given here in the table. Now what is the meaning of specific heat capacity? Okay, specific heat capacity, that would be heat, right? But what heat? So heat needed to increase the temperature of a mass of 1 kilogram, okay, by 1 degree Celsius. So that is the meaning of specific heat capacity. Alright, so next question. Compare the specific heat capacity of liquid X and liquid Y. So just do the comparison. Okay, specific heat capacity, X is lower than Y, right? Or Y is greater than X. Okay, so let's answer this. So remember, you must write down the quantity that is being compared. So here is the specific heat capacity of liquid. Y is greater, right, or higher. Okay, so maybe I can just write here higher lah, huh? Okay, so the specific heat capacity of liquid Y is higher than that of liquid X. Okay, now compare the final readings of the thermometer in liquid X and liquid Y. So we are to compare the final reading. So I write down first the quantity to be compared. So the final readings of the thermometer in liquid Y. Okay, final temperature. So liquid Y is 30, liquid X is 40. So liquid Y is lower, correct? Okay. So the final readings of the thermometer in liquid Y is lower than that in liquid X, right? So I purposely choose liquid Y. Okay, here is liquid Y, down here is liquid Y. Okay, for a good reason later on. Now, compare the change in the temperature of liquid X and liquid Y. So the quantity to be compared is the change in the temperature. Okay, so I just write down the quantity first. The change in temperature of liquid Y is what? Okay, so I go up the change in the temperature. Liquid Y I have 5 degrees Celsius, liquid X I have 15 degrees Celsius. So liquid Y is smaller or lower. Alright, so here is lower or less, okay, than that in liquid X. Now state the a relationship between specific heat capacity and change in the temperature of liquid of the liquid. So we want to do the relationship between specific heat capacity and change in temperature. Okay, so we are talking about this thing here, specific heat capacity, and then change in the temperature. So why I purposely write the same alphabet just now, y here is easier for you to see. Yeah, so if as you can see here, specific heat capacity higher, the change in the temperature is lower. Do you see that? The specific heat capacity higher, the change in the temperature lower. So that is the answer there. All right, so here you can write the higher the specific heat capacity, the lower the change in temperature. Okay, can you follow? All right. So which liquid is more suitable to be used as coolant in cooling system of a car? So as a coolant, so I don't want the liquid to be used to increase in its temperature very easily. So between X and Y, which one will increase more difficult? All right. So here increase by 5, here increase by 15. So meaning to say, if I am using liquid Y as my coolant in my car engine, okay, my engine it will be colder, right? Compared to if I am to use liquid X. If you are to use liquid X, the engine will become very hot. All right. So the answer here, which one is better as a coolant in a car? So the answer here would be liquid Y. What's your reason? Because it heats up slower. Okay, or you can also say the change in the temperature is lower. All right, so you can write any one of these two. So I leave you here for the moment. So we are going to continue with our discussion next time. So I see you. Bye bye.